Log on, tune in, find out. Another good idea from Cambridge.
On moduli space of bundles and Kloosterman sums.
Thank you very much. Yeah, thank you very much for the invitation to speak here. And when I was asked to speak here, I got instructions that I should prepare a general audience talk. Now I see myself with a general audience talk with a very distinguished audience. But maybe at the end of the day, it's not so bad if I sort of try to start with things you all know well, hopefully. And so, but don't, I mean, if anybody has the distinguished feeling that I should have a skip forward, yes, then let me know. Okay, so what I would like to talk about is, finally I want to talk about a joint work of that I did with Gobao Chao and Zhiwei Yun a year ago, and we found an example, an explicit example for where you can get your hands on for geometric Langlands correspondence in one particular situation. But since this is a general audience talk, I thought, well, I just start by motivating what this correspondence is about and how you could, by analogy with modular forms, get to it if you like. Yeah, and so that's where I want to start with, also to give you sort of a bit of a weird perspective on this moduli space of bundles. And in the end, I hope that we will get to Kloosterman sums, which are just purely number theoretical objects, just particular types of sums of roots of unity, which apparently have nothing to do with moduli spaces of bundles and curves. Okay, so let me start with just a reminder on modular forms and what this Langlands program, where it began. So just to just very quickly, you all know. So what is a modular form? A modular form you learn usually is a map from the upper half plane, just complex numbers with positive imaginary part, to the complex numbers, which satisfies this weird transformation property, such that and you have this transformation property for all matrices A, B, C, D contained in some subgroup of SL to Z, which I will call gamma 0. Maybe not very standard. Okay, and so what do you do with these? Well, yeah. So a better way to say this maybe is to say that these are really functions, or rather differential forms on this quotient. And this is forms on the quotient, the upper half plane divided by this group gamma. And so, maybe the main point is then that you can, on the space of all these functions is, these are the modular forms, and you can decompose it into eigenfunctions and according to the Hecker operators, and then the eigenvalues of the Hecker operators are not only supposed to be, but won't magically carry arithmetic information. So let me just remind you how this works in order to translate it to the moduli space of bundles later on. So how do you get these Hecker operators? Well, for this, it's easier to find another description of this upper half plane. So recall that the upper half plane was only SL2R divided by SL2Z, SO2 divided by SO2. And so if you look at this, because this is the stabilizer of the point I, and so if you look at this quotient, then you all know that this parameterizes lattices in C, a lattice after homotopy. That's the let's just write this once. So you have this lattice. If you have a lattice, then you can just turn it to make the one of the, choose a basis, you turn it, the first basis vector to lie on this line, and then you get this element in the upper half. And so if you write it this way, then you easily see how you can produce more functions f out of a given one by these Hecke operators. And they are usually defined for prime p. I don't know, I should write. Well, let me just write off the lattice. And how do you do this? Well, you just take all lattices which differ from your given lattice by a multiple of p. So such that the number of points is p, and you take this thing. And then, yeah, well, if it were really functions on this quotient, then it would obviously be, again, a function on this quotient, and the same goes for forms. Okay, and so magically, so if you have an eigenfunction, if you decompose the spaces of modular forms into eigenfunctions, then the eigenvalues of these Hecke operators are related to two-dimensional representations of the Galois group of Q bar. Yeah, this famous theorem which was announced somewhere here, yeah, I guess, of while. So that's the so maybe let's skip it. Let's note this. So the eigenvalues, they correspond to two-dimensional, and this I'm vague, but representations of the absolute Galois group of Q, which is sort of very strange. Okay, so now there's a, well, this, of course, automorphic forms are a generalization of this, but I want to go to the geometric Langlands correspondence, which is a geometric counterpart of this, and this is maybe goes back a long way. So the point is that there's this analogy of number fields and curves over either finite fields or Riemann surfaces. Yeah, they sort of behave similarly. So let's just try to put up the dictionary of what do we need here in this construction and how we transpose it to the space of moduli space of curves. So let's put the dictionary somewhere. So just from number theory to geometry, and just let me quickly give the dictionary. So what goes into here? So here we have a number field, and what should it correspond to? So here geometry will be we fix the curve. So C, the algebraic curve, or you can think of a Riemann surface is fine for today. Yeah, maybe I just do this. What do we have here? We have this number field, and it mainly appears through. Let me do the list in the good order. Okay. So what went into there? So we had the primes. We had the real numbers. We had the integers. We had the upper half plane, which we found to be SO2R modular SO2. Then we have our group gamma, the quotient, and we have the Hecke operators. Yeah, that's sort of the ingredients we had, and just let's transpose this for the algebraic curve. So what should the field correspond to? I mean, that's the starting point. Is that should be just, maybe I just put K. This is the field of meromorphic functions. Functions on C. Now the primes will just be the points in C. And to see that this makes sense, I mean, if you have a number, if you have an integer, then you would say that p to the some power divides this integer should correspond to the same thing, that you have a function here and that it vanishes to the same order at the point. Yeah. So now we have to. Now we run into a problem because yeah, what is R? So R is just the completion of Q. Yeah. So we look for completions of this field, and there's the only thing you can think of is, well, you just fix a point, which I will call infinity, and then you get a valuation of this point by just saying that, well, you don't just look to the order of poles at this point of a function. Yeah, to every function you can attach a number, which is the norm of the function, is just the order of pole or zero of this function. And if you complete it, what do you get? So let's just stick with the complex numbers. If I complete, then I will get just Laurent expansions at my point pt. So t is so this is completion of k, and t is the coordinate at infinity. Yeah. So that's good. Then what should the integers be? Now the integers should be, well, all functions which don't have poles. Yeah. So don't have poles is not okay, but it's not possible. But outside infinity, it's possible. So I take, oh, these are holomorphic functions. So these are holomorphic on C minus my point. Yeah, but then it's, I mean, once I make this analogy, then it's sort of clear what I have to put here. So the upper half plane will just be SL2 of this thing divided by R. Sorry. Yeah, so I still need this SO2. So SO2 is a maximal compact subgroup here. So, well, if I would have opted for the finite field, then I would know what a maximal compact group is. So I just put the analog. And I claim that this is the analog of a maximal compact subgroup here. Yeah. So if I would have a finite residue field, then this would be a compact ring. So it would be compact, and it's actually maximal compact. And the gamma, so this was in gamma 0, which was just SL2Z. So I just should put SL2 of Z, which was my ring O, and there I should take a subgroup gamma. Some point I will break this. Okay, so now before I go to the Heck operators, I have to sort of understand what is this double quotient H modulo gamma. Yeah? So that's actually a theorem which brings us to moduli spaces, and this is due to Harder and Drinfeld-Simpson. And if I understand correctly, this was conjectured by Narasimhan, or asked by Narasimhan before, that actually if you take this, so if you take G be a semi-simple group, for example SO2, then if you look at this double quotient, divide by this gamma 0, then this is actually gives you 1G. This is the moduli space. Well, it's just the space of all G bundles on C. So this is G bundles So for SL2, it's just the space of all vector bundles of rank 2 with fixed trivial determinant on C. Yeah. And maybe, yeah, I have to put it anyway. And if C equals P1, then G could also be reductive, which is okay. So let me first recall how to read this theorem, or why this isomorphism is actually where this comes from, and that you actually know it for SL2. So how to read this theorem? Well, what is gamma 0? So gamma 0 is just the if I look at SL2, it's just the automorphism group of the trivial bundle over the punctured curve. And the same thing goes here. So this would just be the automorphism group of the trivial G bundle on the complete disk. Yeah, and so this is just the intersection of the punctured curve and the disk. So if I have an element here, then I can obtain a G bundle by just gluing with this thing on the punctured disk. Yeah.
So you're assuming that the bundles are trivial on the punctured thing?
No, the point is, what the theorem says is this way you can obtain all bundles. So the theorem is that even for families of bundle état locally, you can trivialize them whenever you at least take out one point. Yeah. So if you have a G bundle on your curve, take out one point, it will get trivial. And now you look confused, and maybe it's because it's so. First thing.
Okay, yeah. Okay,
right.
Okay.
Right. So that's of course what I should say loudly. I mean, if you think of vector bundles, yeah, then you know that if you take out one point, then you get just a projective module over the Dedekind ring. And then Dedekind tells you, well, it's a trivial bundle plus an ideal. Yeah? And so that's the structures of modulus over Dedekind domains. But if you fix the determinant to be 1, then this ideal is just the determinant has to be trivial as well. So then it's due to Dedekind in some sense. And of course, the thing which worries you is, of course, if I take for the group G just the multiplicative group, then I would get here line bundles on my curve. And of course, on the left-hand side, I will get only line bundles that are trivial outside one point, so I just get O of some powers of P. So the Jacobian is what makes this fail for reductive groups. And that's the reason why it actually holds for reductive groups if I take the projective line, because there's no Jacobian. And yeah, so this was the first remark, and then this was already a few remarks on this, but let me also remind you that this geometric description is actually useful. Yeah, and I mean, if you take the case of the projective line, and you just write out this for SL2, say, then if you look at, you're more ambitious, then you can do this in your head for GLN. You will probably. Then let's just write out what I get here. So then O will be the functions outside this point I fixed. So this will just be polynomials in t to the inverse. So I will get SL2 C t to the inverse. And now I could wonder, what are the double cosets actually? Can I find representatives? Yeah, and you just apply Gauss algorithm. I mean, you are allowed to do column and row operations with polynomials and these things. And then Gauss algorithm tells you, if you apply it cleverly, that you get representatives which are just of the form g of d, g of minus d. For d, well, you can even make it bigger, equal to 0. Yeah, and this is Grothendieck's theorem on vector bundles on P1. Yeah, so this is Grothendieck's theorem. Okay, so now, I think I'm in good time. So Now for modular forms, it was sort of important that you don't stick to gamma 0, because there are very few modular forms. I mean, we know them all, and so you only get more modular forms if you make this group smaller. So the same you would like to do here. So you would like to put a gamma here. So maybe just wipe it out. Yeah, so now let's put a gamma here. And what will I get here on the other side? So I get a moduli space, which I will call Ban G gamma. It's G bundle on C with gamma level structure. And let me, instead of being precise, let me give you an example. So that we'll see, hopefully in this talk, more examples of level structures and what they could look like. So one example would be that you take gamma to be the Iwahori subgroup. I mean, let's stick to this CP1 case again, so that I could take anything here, but here I could insist. So it doesn't matter really, but I could look at this type of things in gamma 0. So what would this mean? What is this the automorphism group of? This is again, I mean, gamma 0 was automorphisms of the trivial vector bundle on the affine line. Yeah, so, and these automorphisms are just those, if I look at infinity, if I put T inverse equals to 0, that they lie in the Borel. Yeah, so it will just be vector bundles. It's the automorphism group of a trivial vector bundle where I have a fixed subspace at the pointer at 0. Yeah, so in general, one example of these objects that you could get is just a vector bundle together with a flag at several points. Yeah, or you could put higher level structure. We'll see this. You put not only flags but even vectors, so bases of vectors, things like this. And then at least for the flags, is there a question? And at least for the flags, I mean, this was the same theorem holds if you put this level structure, and this was a conjecture of so for gamma it was a conjecture of Papas and Rappaport. And it's sort of a surprisingly recent conjecture from this work. Okay. So that's what you can prove. Okay, so now we've seen what this double quotient is, and now the only thing missing is the Hecker operators. Yeah, to say what a modular form is. So what are the Hecker operators? I still have them here, so that's good. So if I now go to curves in geometry, so the first idea would be to just consider functions on Ban G or Ban G gamma. And then I would like to have a Hecker operator, so which should now depend on a point x. And what should I do? So I will call my G bundles E, because I will think of vector bundles all the time, and you should think of vector bundles all the time. So what would the analog be? Well, I write it and then I wipe it out, even if it's videotaped. So so I cannot help it. So I should sum over all vector bundles which are sort of not too much different from the one I started with. And I mean, what does this condition actually mean? I mean, if I have two lattices and the quotient is of order p, then this means if I quotient out at any other prime, I will get this is actually an isomorphism. Yeah. So this should be that I take vector bundles inside my vector bundle, which are isomorphic outside except at x. Yeah? Yeah. So equal on C minus my fixed point. Yeah, and only allow a difference at the point x. Now this is way too large, of course. I mean, I also had this, I mean, this was not the power of p, but it was just p. And so I should fix this. So I fix the type, fixed type. So fixed isomorphism class of this quotient. So if I have rank 2 bundles, I could, for example, say this is a one-dimensional vector space. Again, I mean, if I'm over the complex numbers, this doesn't make sense because there's, I mean, if I, for example, if I would insist that this is isomorphic to C, then, yeah, this was just the sum of a projective line, so I shouldn't put a sum. So I shouldn't. So maybe I should sort of, so for finite fields that the sum would be fine, and otherwise I should say sort of take an integral. And then I should tell you what the measure is. And then I'll say, well, I will not do this because that's not the right thing to do anyway. But that's a better way to do it anyway. And that's, yeah, this I have to sort of sell to you in some way. It's better to go from functions to sheaf. So and a sheaf, you can either if you know what it is, you can think of perverse sheaves, or of D modules. So what is probably easier to sell this is the D module story. So what is a D module? A D module is just a coherent sheaf with an action of the differential operators. So what you're essentially doing here is saying, well, you're not looking at functions, but you're looking at the differential equation that the function satisfies. Yeah, and this is for an algebraist. This is sort of nicer because the algebraist also wants to have an exponential function after all, which is not algebraic. But the differential equation it satisfies is algebraic. Yeah, so that's sort of the easy way to sell to go to D modules, and we'll see other motivation later on. Yeah, so and then I get rid of this integration procedure, as we have seen sort of several times, I think, today. Then I can, yeah. So then I can. So I missed one thing I wanted to say. So if I want to define what T of X is, well, I just, what do I say? I mean, I take Bun-G, so then I take all, so let me just put it right. So. And relative position at x fixed. I'll come back to what I mean, but what I just mean is, again, in this simple example, just all these modifications of a bundle at a point. And then I want to sum back to Bun-G gamma. So here I project to, now I have to do it. So in this way, so this maps to E. So this is people call Q. Let's call this P. So this maps the whole business just to E prime. And so what I want to do is, well, I want to sum over the fibers of this map. Yeah. So what I just do is I have a sheaf here, I pull it up and push it forward here. That's essentially what I want to do. Yeah. That's this integration procedure would just be a push forward for sheaves. And then there's a nice observation that I can make here in this diagram, is that here, if once I end with sheaves, I can let this point x vary as well. Yeah. Yeah. I mean, I can. That's a big advantage over the prime numbers. That now I can let the point x where I allow to modify my bundle, I can put it into the datum as well. Yeah, just take an X here and such two things. And then this will not only have a second map to band D gamma, but also a map to C. Yeah, so now for all different points, the Hecker operators come into the family. Yeah, and so this T of X will roughly be you pull back and you push forward. Okay, I have to make one comment, and this is now, I sort of switch to groups. So I have to sort of motivate what relative position means. Yeah, and so in this simple example, this was a very easy way of saying what the relative position is. It's just a line. Yeah. So what is relative position? So if you look at this more closely, then you see that actually I was lying all the time if I do SL2. Yeah, because if I take a vector bundle and modify it at one point and the determinant was trivial, then after it will no longer be trivial. So for vector bundles it would be okay, but for SL2 it would not be okay. So I really have to resort to this definition in some sense. And let's just do SLN or GLN. For this, so I have to say, what is how meromorphic is this isomorphism locally at X? Yeah? So locally at X, if I call this isomorphism phi, so phi will be a morphism from the trivial bundle to the trivial bundle on the punctured disk. So locally at X. So I go to the disk at X, and I call the local coordinate at X. What should I call it? So this is so a coordinate on the with coordinate. Say Z to distinguish it from the T that we had all the time. So then phi would be a meromorphic map from the trivial bundle. So if I fix the basis, and just by just the linear map, which is only defined on the if I put round brackets, yeah. So, but by the elementary divisor theorem, so phi will be conjugate. So if I choose good basis on both sides, to actually a matrix which looks like this, and with D1. Say larger or equal to dn. And if you're in the SLN case, and for SLN, you might want to put that the sum of the di is 0. Yeah. So the possible relative positions are just given by sequences of this form. Yeah. Yeah. So the relative positions will just be given. The relative position. Well, I just say such an isomorphic is in relative position these numbers if it's actually conjugate to this matrix. Yeah? So for example, if I put just T111, then I will just get the modifications that I had over there. Yeah? And so the relative position, and if I look at such things, then I could say, well, this is actually dominant one parameter subgroup. Of a torus in G. So if I take a map from the multiplicative group into T, then this will give me such a thing, maybe not ordered, by just plugging in T into it. So, and I will call this, such a thing I will call lambda. And so my Hecker operator will depend on the choice of lambda, and the relative position I will fix lambda. Yes? Okay, this was maybe already too technical, but this is sort of the analogy of higher dimensional Hecke operators that we have. Okay. Okay, I have a lot of time. So now what would be an eigen? So what is now an eigenfunction? Well, it should just be, yeah. So it's videotaped, so I have to say that I lied a little bit. But I put these quotation marks here. So yes. So if I really want to do this, then I have to compactify this. And then I also have to not just plainly integrate, but first multiply with people call the intersection complex on this thing. But it doesn't matter. So morally, it's just pull back, push forward. And I mean, in this case that we were considering of GL2, where I just considered these simple modifications, there was no need to compactify because the fiber was a P1 bundle. Yeah, so there was no.
Does this send sheaves to sheaves, or do you have to also do this now in the derived category?
Yes, of course. I mean, when I call perverse sheaves, then I'm sort of living in the derived category. And what I want of an eigenfunction is that this Hecke operator actually lands in the heart again. So, but there's no a priori reason why it should do. So an eigenfunction would just be a perverse sheaf A on band G gamma, so such that, and here also I hide some technical details just for, it's complicated enough, I think, such that, well, if you apply such a thing, now that I put it into the family, I can drop the x. It's no longer fixed. So what will this be? Well, it will be a sheaf on this, or a complex on this product. So what would eigen mean? Well, on the first factor, it should just be what it was. So it should be of the form A, and then tensored with something which only depends on the point. So if you take a projection of C upper star of something, and this something will of course depend on lambda. Yeah, where V lambda is a perverse sheaf or a D module, so it's a local system. Let's see. Now I was sort of mixing. Yeah. So that's sort of the idea. So what does multiplying with a scalar mean for a sheaf? It just means multiplying by a vector space, and this vector space is allowed to vary with the curve. And if we are lucky, then the dimension of this vector space will not change with the point that we do. Now there's one thing that I did badly here. And this was this thing that I said that this was all fine if gamma is gamma 0. Yeah? So if I'm really talking only about G bundles without the level structure. So if I put the level structure, then this relative position will get refined. Yeah? I mean, if I have two vector bundles and they both come with a flag at these points, then it's not only what's the quotient of the map, but also how is the relative position of the flags. So this will give a headache. So we will not do it. So we will just take out the points where gamma is not gamma 0. Yeah. So I will just replace C by U, where U is some open subset in C, depending on gamma. Yeah. So at those points where I haven't put a level structure, this makes perfect sense. And so then I wouldn't have the eigenvalue, which will only be a local system on U, which corresponds to the fact that for modular forms, you would also expect to get a Galois representation. I mean, you cannot possibly expect it to be unramified everywhere, yeah, because these things do not exist. And so you also want to have local systems on the punctured curve. So that's an eigensheaf. Now there are two comments that I want to make. The first comment is that there are very, in contrast to modular forms, there are extremely few examples of such objects which are explicitly known. Yeah, and this, yes. So it's terribly hard to construct them. And the constructions that exist are most of them are very complicated. So you cannot. It's very hard to compute what you actually get. I mean, what is this complex you will get on Bunch gamma? And that's sort of a pity because for modular forms, I mean, the beauty of the theory is sort of that you have these modular forms, and whenever you find somewhere a modular form, you get interesting extra results. So you should go and look for them. And that's what I want to do. But before I can state this, that this simplest of example that one could think of, I should note that what is actually this eigenspace? Yeah, so I get get a V lambda for all lambda. So can I put this collection of these local systems for all lambda sort of into one set of data? Yeah, and this is, of course, you say, yeah, of course, because I mean this is just the d1 up to dn. This is just parameterizing a reducible representation of GLN. Yeah, if this was GLN, so I just get there should just be a GLN local system on my curve, such that this V lambda is the associated representation. Yeah. Now, but if you look more closely, then you see, well, this is not really what you should do, because irreducible representations are parameterized. I mean, they are parameterized by highest weight, so it's not one parameter subgroups of T, but characters of T. Yeah. So here you have to switch to. So this should give you a local system. This should give you a local system for the dual group. So where this is the Langlands dual group, well, so there are various ways of defining it or calling it, and I just use the check for it today. And so let me just give you a very silly example, which sort of only to illustrate the point that I want to make. So really I should talk about roots and co-roots, but I don't want to. So here I have the one parameter subgroups, which are only given by t to the d and t to the minus d. And in PSL2, I would have much PGL, no, let's call it PGL2. I have much more one parameter subgroups, yeah? So here I only have these where the difference is even, and here I have all differences. But on the contrary, if I look at the irreducible representations, here you get all symmetric products. And here you only get the even symmetric products. Yeah, because only on the even tensor powers DL2 will actually act. Yeah, so here you have fewer subgroups, and here you have more representations. Yeah, and so this numbering of Hacker operators with the one parameter subgroups really corresponds to getting representations for the other group. Yeah, so there's this, and that's sort of the beauty of the geometric story, that you can actually see where this comes from, this duality. Okay, so now I want to put the theorem I want to talk about. And this theorem has some history, of course. I mean, this was the way I presented it is really unfair, because I tried to make it. Yes. but I anyway. So this is joint work with Jochen and Duisburg-Essen. And I give it vaguely. So I fix the curve to be P1, and I will comment on this. And for every reductive group, G, there exists an explicit eigensheaf A. No, yeah, let's call it A. It depends on. It depends on 1 G gamma 02, and I will explain what this level structure is. And its eigenvalue which we call KLG check is a G check local system. Yeah, now I have to. Yeah, you will not like it, but that's the truth. I just take out 2 points, and now comes something that you. But it's so. That's the theorem, but the theorem is also that this is actually not. It's actually a very interesting local system. So a local system is essentially a representation of the fundamental group, where I now think arithmetically, or in the D-module sense, it's the differential gamma group. So whatever, it's a representation of the fundamental group, so I can talk of the monodromy of this representation. And this is actually huge. First, it has large monodromy. So in G, it is dense in E8, if you put E8. And I mean, I could give you all this, but let's just put the biggest. And second, there's no, you cannot deform it infinitesimally. So there are no it is cohomologically rigid, no infinitesimal deformations. Admits. Yeah, you cannot deform it. And that's actually a, yeah, so that's the theorem. And maybe I should comment. So, yeah, so now, really, I do this over a finite field, but we could also do it with the complex numbers in the D-module setting. So then this rigidity of this thing, that you cannot deform it, was actually a question which was asked by Nick Katz. So Katz studied local systems on P1 minus a few points, and was looking, and he constructed a lot of local systems that you cannot deform. Yeah, and then he looked at what their monodromy group is, and he found some interesting monodromy groups like G2. And he was and in one of his books he was asking whether actually these exist for all exceptional groups. Yeah, and so here we almost give it for all exceptional groups. There's some, since as I will indicate, the construction is very, very functorial. So if you have a diagram automorphism, then you cannot expect to have the full group. So G2 and D4 will have the same closure of the monodromy group. And we actually conjecture that these are actually the same sheaves, so they really come from a morphism from D4 to, from G2 to D4. But yeah, this we cannot prove. So
I mean, at first it's not clear what large monodromy means over the complex numbers. Looks like you do it.
yeah, so large monodromy is really on the Dow fundamental group, and here, well, here I think the proof would give that the differential Galois group is big. And actually, I mean, this has a history, of course, as I said. So this was originally, there's an article of Gross and one of Gross and Frankel. And so Gross found, using the trace formula and complicated arguments, that for this type of level structure, there would be a unique automorphic form with certain local behavior. Yeah, and he was asking whether, what the corresponding sheaf is. Yeah, and so, and in particular, what the corresponding local system would be. And so Frankel and Gross wrote an article together where they said, well, maybe we can say what it should be of the complex numbers. So by analogy from the finite fields passing to the complex numbers, and then assuming that there would also be such a unique automorphic form, assuming Langland's conjecture, there should also be a local system. And what they do is actually they construct by hand a D module on P1 minus 2 points, which has the expected cohomological properties. Yeah, but it's a sort of, the other side of the story was purely conjectural. And yeah, so that's what we found. And maybe in the last 10 minutes, maybe I try to spend them equally. So first, I want to give two things. One thing, I want to give a brief idea on how you find this explicit eigensheaf and why it's not complicated to construct. And second, I start with the second because my time is approaching its end. It's the relation to Kloosterman sums that I promised. Yeah. So let me give an example. So if we take P1 of the finite field, then, and you take for the group G equals G on N, then this Kloosterman thing is the linear Kloosterman sheaf. And what does this mean? So what is Kloosterman sheaf and what are Kloosterman sums? So maybe I start with the Kloosterman sums. So the Kloosterman sums. So if you have an A in your finite field, and let's take it Fp, then I skip a trace. This is the following sum of things. So you look at all n tuples of numbers which multiply up to the number you fixed. So Ai in Fp. And then you sum over the root of unity, which is given by the sum of the AIs. So that's a Kloosterman sum. So these are just roots of unities. And this is a very weird way to pick roots of unities. Yeah? You fix the product, but what you evaluate is the sum. And Kloosterman found these sums.
N factors.
Yes, it's n factors. And Kloosterman found these sums actually in a classical problem where he used modular forms. I mean, what he wanted to do is count in how many ways can you write a number as sum of 4 squares. And then, well, these type of questions you try to answer using modular forms, and then he found these things, and what he needed to do was find a good estimation for this. So on average, you will expect this to be 0, because whenever you take a random sum of roots of unity, on average it should be 0. But the problem is this could accidentally be large. Yeah? And so the linear is bound, and this is what follows from the theorem. Follows again from this theorem is that this absolute value is actually smaller than q to the n minus 1/2. So no, p. And this is actually an optimal estimate, at least if you put q. So this is the linear estimate. And this again follows from our theorem in a funny way. Namely, well, how did Deligny prove this? Estimate. Maybe very quickly. So the point is that over finite fields, so if you're over FQ, then if you have a local system, you can cook out a function on your object that you have. So if you have a representation of some Galois group, so some local system, then you can cook out a function, because I mean inside here you have the Frobenius, well, at least its conjugacy class at all points in X, so for all X in X, then you can just map it to this element, take its trace, and this will just give you a number. So this tells you that starting from a local system, you can get a function. And Grothendieck proved that this correspondence is very nice. Namely, the Grothendieck trace formula tells you that if you do such a thing, pulling back is just pulling back of the functions. This is pretty obvious. But pushing forward, well, since I compactified, pushing forward will just actually take the sum over the fibers, just as we wanted to. Yeah, and so Deligny got this estimate from looking at the following. You just take the multiplicative group, or no, let's take A1, and what you want to do is sum all roots of unity where the product is fixed. So you have a map. So take AN, go to A1 by the product map, and you go to A1 with the sum map. And then on this, there's a sheaf which I would call X, which is called the Artin-Schreier sheaf. But this is just a local system on A1, such that the trace function will just be at the point A, it will just be e to the 2 pi I over PA. Yeah? And then he said, well, this Kloosterman sheaf N, this should just be, well, you do what you should do. Yeah? You take the product map, sum of the fibers, of this exponential function. And yeah, and then he proved that, well, this is actually this way. If you do this to this sheaf, then you actually get a local system. Yeah, so you really get a representation of the fundamental group. And he proved that it is a pure local system, which gives you this estimate. Yeah, and then he proved it's a local system. He proved that it's of rank n, and he proved that yeah, and this gives you this purity. Then gives you this estimate. But its proof is extremely beautiful. I mean, it's really, I mean, this is really hard. Yeah, and what the point here of why does this follow from our theorem is that actually this correspondence shows up as a Hecker operator in this in the case of GLN. So this actually this arises. No, I just say it in words. So this diagram arises as a Hecker operator, and our proof is sort of funny. It does not do so much computation. It says that we take our automorphic sheaf, we prove by abstract, more or less by abstract nonsense, that it is really an eigensheaf. So then we will get for all these lambdas such a local, first you only get a perverse sheaf, yeah. But then you say, well, but then you get it not for all lambda, but you also get it compatibly with the lambdas. So it really gives you a representation of this group by Tanakayan formalism. And it's a very, so by looking not at the single Hecker operator, but at all of them together, you get that the eigenvalue must be a G-hat local system without further computation, just from Tanakayan formalism. So you don't need to compute anything to prove that this is a this is really of rank n. It's just because it cannot be otherwise, because it comes from this nice tensor functor. Yeah? And this is sort of a computation-free proof in some sense. Well, there's a lot of theory going on of this thing that it's really pure. And maybe I don't tell you how the sheaf comes about, or maybe I have half a minute. So, but the idea is pretty clear, I guess, even in half a minute. If you look at SR2 and P1, then you see that you have a discrete number of things. And the generic bundle will just be trivial. It will just be the trivial bundle. So this trivial bundle is sort of an open substack here, and it is automorphisms your whole group. So if you put some level structure at 0 and infinity, at some point all these automorphisms will be rigidified. So your moduli space will just be a point. And then you have to go, this level structure that Gross suggested means you go one step higher, and then over this point, so the coarse moduli space is just a point. Over this point you just have an affine space. And on this affine space you just put the exponential function, and that works. Yeah, so this sheaf is really supported on an affine space sitting in this bun, and on this affine space it's just the exponential function. And because all other because it's the exponential function, it has an equivariance property respect to adding, respect to addition, and all other bundles have an automorphism which is non-trivial. So however you extend this exponential function, it must vanish on these other points, because it has to be something which is has a non-trivial equivariance. And this gives you that it's an eigensheaf. So, but it's a very simple thing. I mean, it's just because the moduli space is so simple. So it's essentially also this, So what you would expect is that this rigidity of local systems just stems from the fact that the moduli space that you have is essentially zero-dimensional. Yeah. So thank you.
Any questions? Okay, if there are no questions, then can we thank you?